Okay, this is 5.4. We're going to go over number 23. We did this in class, the video glitched, so I'm going to give it another shot just because I know we had 3 people absent today. So if you look at it, what happens when we get in these problems toward the ends of the exercises is they're trying to get us to see some things by having us play around with the numbers. And some of these definitions are in the section, but I'll just go over them again and explain them. Okay, 5.4, number 23. A says write the complex conjugate of 4 plus 7i. Now, this 4 plus 7i, it's based on that thing they told you about, that in the complex numbers, which means there's a real part and there's an imaginary part. We have an a is our real part, and we call the b, the coefficient of I, the imaginary part. And we actually, in class today, if you were absent, we learned that we could graph these numbers by calling the x-axis the real axis and the y-axis the imaginary axis, and you would graph A, B, just like it were a point, except the x part is the real part, the A part's the real part, the B part's the imaginary part, and if you just graph it as if it were x, y, you'll get it down right. All right, we have A plus BI. What we learned that the conjugate was, and we went into a lot of detail that I'm not going to be able to go into here. Just you might. There's just so much we could talk about it, and it's not going to fit on one video. 4 plus 7i. If I want the conjugate of that, I write down the first number 4. I write down the 7i, and all I do is change the sign in the middle. It's a plus or it's a minus. That's 4 minus 7i. Now the B part, they want you to just again practice writing conjugates, and we're going to see in a minute what happens when we have conjugates and we do things with them. All right, 3 minus 8i. If I want the conjugate, let me write conjugate down just so you realize this is the work here. We write down the first part, which is 3. We write down the second part, which is 8i, and we just change the sign in the middle to plus. Okay? Now, if you go on to C, I'm going to go on. They want us to multiply 2 conjugates, and so 7 plus 3i, you might recognize that number from number 1 if you watched the video from number 1. It was one of our answers, actually. And 7 minus 3i. Again, this is a plus here. If you're looking in the book, you should see what it is. It's just that, again, if I hit undo on the iPad to erase that, it glitches the whole video. That's one thing I've learned here lately. So if I multiply these things together, let's see what happens. 7 times 7 is 49. 7 times negative 3i is a negative 21i. I is really a number. It's the square root of negative 1. But when we're multiplying it, we're just going to treat it like it's a variable for now. All right, now I got to distribute the second term. Positive 3i, weird looking positive, I know. I'll try to write a plus over it. Plus 3i times 7 would be plus, oh my goodness, plus 21i. And then plus 3i times minus 3i. A positive times a negative is a negative. 3 times 3 is 9, and I times I is I squared. Now you might already notice that something's going to add up to 0 here. Negative 21i and plus 21i add up to 0. So this leaves me 49 minus 9i squared. Okay, but I don't want to leave it like that because I can simplify it. One thing you should have seen either in the book or from listening to the videos if you were absent is that I squared is equal to negative 1. So this little I squared is equal to negative 1. That's kind of our bridge between real numbers and complex numbers. I can now say that's 49. Okay, a negative 9 times a negative 1 is a positive 9. So those numbers equal 58. When you have a complex number like 7 plus 3i and you're working problems, its partner 7 minus 3i always shows up. If 7 plus 3i is a solution, 7 minus 3i is a solution, because you think about it, when we get equations, they're all real numbers as coefficients. These i's are only coming in because we have, when we do the quadratic formula and we solve those kinds of things, we end up with stuff that's not perfect squares, but we can break them apart this way. Part here says do the addition. Now I'm going to tell you this part's not nearly as important as the part we did before. As a matter of fact, I'm not quite sure why They're asking you to do this because honestly I haven't run across it in teaching any of the classes that I teach, and I'm not sure why they're making such a big deal about it, though I know all books have you practice adding them. It's like adding like terms. 11 plus 11 is 22, and positive 5i and a minus 5i, they add up to 0. We could say they cancel out, but we get 22 there. So notice when we add them we get a real number. When we multiply them we got a real number on C. When we added them we got a real number on D. Probably we're going to get a real number on E because it asks us to subtract them. So let's see if that happens. It seems to be the pattern, and that's what they're wanting us to notice, is that there's a pattern here. Now before I do this, I need to say, ooh, there's a minus sign in front of that parenthesis, so the subtraction sign goes with each term. I can say that's a minus 6, and a minus 10 is a plus 10i. Remember, if that confuses you, remember that you can put the little invisible 1 in there, and you can distribute it. Negative 1 times 6 is negative 6. Negative 1 times negative 10i is positive 10i. Now let's see what happens here. When we added them, we had a whole number answer. When we multiplied them, we had a whole number answer. But let's see what happens when we're subtracting here. I have 6 minus 6. Ooh, the real number part goes away. I have plus 10i and plus 10i. That's plus 20i. So when you subtract them, you don't get a whole number. Again, I'm not sure why this is so important, though I guess someday in some advanced math you may run across this, or they wouldn't be pointing it out. Again, I have not noticed it all the way through calculus as far as why we would do this. I do know that all books, again, require you to know how to do that. So F said prove that the sum and the product of two complex numbers is always a real number, and the difference between a complex number and its conjugate is always a pure imaginary number. We're going to stick to just proving that if we multiply a number and its conjugate. I'm just going to do one of those, and you don't need to worry about the other one unless you just want to do it for fun. Here, if we want to prove it, what we do is we're going to have to describe any complex number and its conjugate. So if I have the complex number a plus bi, its conjugate would be a minus bi. Now, so now that's what we're given. Now, what happens when we multiply them? Well, we can do the distributive property. We know that's okay to do. So when we do that, we get a squared minus a bi. Excuse me. Now I'm going to distribute the bi. Bi times a. Positive times a positive is a positive. And if you put all those numbers down, and we usually just put them in alphabetical order, you get a bi. A positive bi times a negative bi would be a negative b squared I squared. Okay, so all that was just the distributive property. So on my next step, what I'm going to do is just combine. I'm going to notice that I've got these things here. They're opposites. So on the next step, we would have those add up to 0. And then we'd have minus b squared I squared. And the reason that's true is you can call it the property of opposites. You could call it additive inverses. I'm going to call it additive inverses because most books call it that, though your geometry book last year called it property of opposites. Now a squared plus 0 is just a squared, and I have minus b squared I squared. When we add 0 to something, that's just the additive identity. Do you remember? So that's why that's true. Again, we're just given a reason for every little step that we do. All right, now, by definition, I squared is equal to negative 1. That's just definition of I squared. Some mathematician a long time ago decided that that's how he was going to talk about these numbers, and he just said I is square root of negative 1, and so I squared is negative 1. Okay, so now I've got a squared minus b squared times minus 1 is a plus b squared. So that is just because, let's say, multiplicative inverse. No, multiplicative. That's just multiplication. Duh. Just multiplication. Just say multiplication here. Now, if you have a number it doesn't matter if the number is positive or negative. You square it, you're going to get a positive number, right? If you have another number, b, whether it's negative or positive, when you square it, you get a positive. And when you add two positives together, you get a positive number. Therefore, the product of these numbers is actually a positive real number. Okay? And I'm going to stop with that. You don't even worry about the proofs on the other ones, but you just need to at least understand up through what I did here on the video if you were absent.